In this video, we're going to do example 3.4.1, and we're going to do a couple of examples where the tangent plane is not well defined. Let's first start by reading definition 3.4.2. If P with coordinates ABC is the point of tangency shared by a surface S and its tangent plane T, what we studied in a previous video at P, then the normal line to S at P is the line passing through P with direction perpendicular to T. So in the next example, we are asked for the tangent plane and equations for the normal line to the surface f of xy is the square root of x squared plus y squared at the point 3, 4. So the first thing that I'm going to do, because I know that we'll need it, is calculate f of 3, 4, which is going to be the square root of 9 plus 16, which is the square root of 25, which is 5. F sub x, the partial with respect to x, we're going to use the chain rule, so 1 over 2 times the square root of x squared plus y squared times the derivative of the inside with respect to x, which is going to give me 2x, and so the 2's here and here cancel out. I'm going to need f sub x at 3, 4. If I plug that in, x is 3. The bottom is still going to give me the square root of 25, which is 5. F sub y of x, y. We'd spoken in a previous video about symmetry. You can either do the calculation again or realize that you are just going to interchange x and y. And so we have f sub y of xy is y over the square root of x squared plus y squared, and f sub y at the point 3, 4 is the point, or the fraction, 4 over 5. We want to give the tangent plane and then the normal line. So let's start with the tangent plane. We have a formula for the equation of the tangent plane, and that is z is f of AB plus f sub x of AB times x minus a plus f sub y of AB times y minus b. Our AB is the point 3, 4, and so we are going to have z is f of 3, 4 plus f sub x at 3, 4 times x minus 3 plus f sub y at 3, 4 times y minus 4. Z is 5 plus 3/5 x minus 3 plus 4/5 y minus 4. And we would be done, except that we are asked for the equation as a general equation, and so we must we must bring the variables all to one side and the constants all to the other, so I'm going to multiply everything up by 5. So I'm going to get 5z is 25 plus 3x if I multiply that through, 3x minus 9, plus 4y minus 16. Those will cancel out as constants, and if I bring the z over to the other side, I'm going to get a general form equation of 3x plus 4y minus 5z is equal to 0. Now I haven't left myself a whole lot of space here. Let's maybe carve out a little bit for the normal line. We're asked for the parametric equations for that normal line, and so we're going to have x, y, and z equal. They will pass through the point that we know, and that is the same point that we have a, b, and f of AB, so the point 3, 4, 5. And we're going to have as direction of the line the normal vector of the plane. So we're going to have plus 3t plus 4t and minus 5t for any variable parameter t, value of t in R. Let's take a quick look at some examples where the tangent plane is not well defined. So the first here is a sharp point in figure 3.4. The second is a deeply folded surface. So in figure 3.4a, we see a sharp point, which is the analogous kind of surface to a sharp point that you might have seen in your first calculus course. The derivative did not exist in that kind of sharp point in calculus 1 and does not exist in this kind of sharp point in three-dimensional calculus either. In figure 3.4b, this folding surface doesn't look like it's particularly badly behaved, but actually it is. If we look in the figure, we can see that the function value on the axes, the function is completely on those two axes, the function value is 0. So along each of the axes, in the direction of that same axis, the function value does not change. So the direction, so if we start at the origin, the direction, right, the change, instantaneous rate of change in the x direction would be 0. And from the origin again in the y direction, the instantaneous rate of change would be 0. So both partial derivatives would be 0 at the origin. The origin is also on the surface graph, and so if we applied the tangent plane formula that we just did in the previous example with AB at 0, 0, we would get z is f of 0, 0. That is 0. Plus the partial at the origin, we just said that that was 0. Plus the partial at the origin in the direction of y. All of this is 0. We get the plane z equals 0 from the formula. That doesn't mean that the formula is actually giving us the tangent plane. It's giving us a plane, but it's not a tangent plane. How can we see this? If we look at the instantaneous rate of change of the function up in the direction of, let's say, y equals x, look how it goes up steeply in that direction. It's flat here, yet really steep up in there. The xy plane, the plane z equals 0, is not a good match for the function up in that direction. The tangent plane is not well defined in this case, and we will show algebraically later in the section that it is actually because this function is not differentiable at the origin.